Okay, so this is chapter number 11. It's about the inductors. So see here. So here is the YouTube the links where you can get more information about what is inductor. You can, this is for your reference. We can start from the basic inductor. So basically, when a length of a wire is formed into a coil, it becomes a basic inductor. You know, you have a lengthy wire. If you make it a helix shape or this is a coil shape, it's basically become a basic inductor. So when there is a current in the inductor, a three-dimensional magnetic field is created. This is the property how the inductor basically works. So whenever a current is flowed in the inductor, a three-dimensional magnetic field is created. Okay, as you can see here, south and north, you can see here. So a change in current, the flow, which is the current which is flowing here, a change in the current causes the magnetic field to change because that magnetic field is developed because of the flow of current. So if the current change, okay, so the magnetic field is also change. This in turns induce a voltage across the inductor. Because of this change of the magnetic field, a voltage is induced across the inductor that opposes the original change in the current. Actually, that voltage which is induced, it opposes the original change in the current. So this is what we discuss. It's the basic phenomena which happen in the inductor basically. So 1 Henry is the inductance of a coil when a current changing at a rate of 1 ampere per second induces 1 volt across the coil. Most coils are much smaller than the 1 Henry. That is like 1 millihenry, microhenry, okay, picohenry, like that. So we can have a this coil wound on a magnetic core that is basically enhance the magnetic field basically when we have when we wound this turns on the magnetic core. So the effect of inductance is greatly magnified by adding turns and windings, winding them on the magnetic material. Large inductors and the transformers are wound on a core to increase the inductance. Four factor basically affect the amount of inductance for a coil. The equation for inductance you can see here given. So L is equal to N square mu A over L. What are these? So where the L is inductance and the unit is henries, and then a capital N here, uppercase, number of turns of a wire, and mu is the permittivity in Henry per minute, Henry per meter. And then we have L, coil length in meters. So just to apply this formula, we have this one. I believe that you have already studied all these things in the physics course, but it is just a review. So what is the inductance of 2 centimeter long 150 tons wrap on a low carbon steel core that is 0.5 centimeter diameter? The permittivity of a low carbon steel is 2.5 into 10 to the power minus 4 Henry per meter, or Weber per atom per meter. We can also show this way. So first of all, we need to find the area of a circle. We know that pi r square because the wire is a circular shape, and then we have need to convert it into meter square, and then we can apply in the formula, and this is the solution, and we got the value L is equal to 5.5 millihenry. Okay, so after knowing the basics of the inductor, now multiple conductors can be connected in series or can be connected in parallel, similar to we have discussed for the capacitance in series, capacitance in capacitor in series, and capacitor in parallel. We have seen already in the chapter number 9 and 10. So when a capacitors are connected, when the inductors are connected in series, the total inductance is the sum of individual inductors. The general equation for the inductor in series is LT is equal to L1 plus L2 plus L3 up to Ln. So this formula is similar formula which we use for the resistance in series, right? It is similar to that one. So we can have a question when we have in, so whenever you have a different prefixes, you need to convert it into a common one, and then you can convert it. So it's just a simple addition after having a common metric prefixes of the given value of the inductor. So when inductors are connected in parallel, the total inductance is the smaller than the smallest one. Same rule which is applicable for the resistance. The general equation for the inductance in parallel is, you know that one, inverse of the sum of the reciprocals. So total inductance of a two inductors is given. Now you can apply the product over sum rule, that you can also write LT is equal to L1 L2 over L1 plus L2, which is again similar to the resistance formula. So we call this one product over sum rule. So two inductors are connected in parallel. We can apply the product over sum rule, and we can find after converting the common metric prefixes. So similar to the capacitor, inductor can also store the energy in the form of magnetic field. Like for the capacitor, we have seen that it can store the energy in the electrostatic field in the form of charges. So we have seen that how the capacitor charge and how capacitor discharge. Similarly, here we can discuss that how the inductor stores energy, any charge, and how it discharge. All right. So here we have LR circuit, which you can see RL circuit, we can say, and the time constant we'll be discussing here. So the time constant which we have seen for the capacitor, we have the similar time constant here. Okay, so for the capacitor it was tau is equal to R into C. But here what we have tau is equal to L over R. Okay, this is the time constant. So we can see here, here the how the inductor stores the energy. Actually, it stores the energy in the form of, we can say, current. Like for the capacitor, we have seen it stores the energy in the form of voltage. In general, we can say it is stored in the form of current. Okay, so here we can see this graph, which is here. So in this graph, we can say it is a charging, like the how the current is set up in the inductor. So it's increasing from 0 when initially we can say, the switch is open. And as we close the switch, we can say that inductor start charge, it's charging, like current start storing here. So how it is start storing again, it is a rising exponential, and it reached to the 99% value, or this one in a final IF value by after 5 time constant. It is similar rules which we have discussed for the RC circuits. Here we have discharge concept, like when the inductor is fully charged, okay, it can we can also discharge it. Again, the same circuit, will be removing this battery, and the direction of flow of current will be reverse, and the inductor will discharge. So the current which is stored in the inductor start basically reducing, which is what we call falling exponential, and reach to 37% of the initial value in one time constant, two time constant, and 5 time constant. It completely discharge, we can say like this. All right. So this is the formula for the time constant for RL circuit, which is L over R. Okay, so this is the difference. For RC, we have R into C. So again, here as we can see that what happening, as inductor start discharging, we can say it reach to 0. So there is something which is basically blocking the flow of current, opposing the flow of current. So there is an again reactance which is similar to the reactance in capacitor we have seen. So here we call the name inductive reactance. And what is that? It is the opposition to AC by an inductor. The equation for the inductive reactance is here XL is equal to 2 pi FL. Okay. And you hope you remember for the LC, it was 1 over 2 pi FC. XL 2 pi FL. Okay. So this is the change. So we need to find the inductive reactance. We must know the inductance. We must know the frequency, and then we can calculate it. So the unit is again same, ohm as the capacitive reactance unit. Now, so universal curves, we have already discussed this equation for the voltage, okay, instantaneous voltage in the capacitor. Similar form, instead of V, you are just replacing with the I. So I is equal to IF plus I minus IF e raised to power minus R, R divided by tau, T over tau basically. And tau is what? Tau, we know that it is L over R. So R will go up and L will be go denominator. So IF is the final value, II is the initial value, and I instantaneous value. So the final current is greater than the initial current when the inductive field is building, or less than the initial current when the field is collapsing. So rules are same, which we discussed for the instantaneous voltage in capacitor, and here is same. So final any value, so whatever when it reach to the maximum current, any the total current, it will reach to that, and initial current will be the zero when we are considering that inductor is charging. When it is discharged, so final value will be zero. Okay. So let's have a question to understand that one. So question is this: calculate the RL time constant, and then determine the current and the time at each time constant interval measured from the instant the switch is closed. So initially when the switch is open, so inductor is discharged, there is no current. Okay. Now what happening after that? So what we can do? First, we need to calculate the tau time constant, and we know the formula, which is L over R. So just put it and we'll be getting 8.33 microsecond. Now, we need to calculate the final current. So final current is how can we calculate the final current? So when we close this switch, so what happened after a long time, or after some time, yani after 5 time constant, we know that the inductor will be completely charged. So basically the point is that when the inductor is fully charged, it becomes short circuit, means all the current will pass through it. It will be like a short circuit once it is fully charged. So when it is a short circuit, it means there is no resistance. So only resistance available in the circuit will be the R. So the total current, okay, or what we can say, the final current, what it will be, IF Vs, any total voltage divided by the resistance in the circuit. So inductive reactance will be zero at that time. So there is a reason behind, okay, because of long time what happened, it's become fully charged. When it is fully charged, so it's behave like a short circuit. So because of that reason, we can simply calculate the final current Vs over R, and we are getting the value here 10 milliampere. Okay, so this is the final current. Now, so once you know the final current, we can calculate the current at different instant of time. So we have solved similar question for the RC circuit, but here is a different way. So we are using here the exponential curve. Okay, if you remember the exponential curve, what we did, exponential curve, here is the exponential curve, and if you look here, so in one time constant, it charged to 63%, two time constant 86%, three time constant 95%, and four time constant 98% of final value, right? And now we already calculated the final value in that question. So we can just, in one time constant, it will be 63% of the final. In two time constant, it will be 86% of the final. So this is what we are going to apply in, we can also apply this way if we know these values. If we don't, we can simply just put the value of t in the equations and we continue. So we are looking for the charging. So it means that the initial value, any II, will be 0. So when I put II as a 0, it will be IF. Okay, any IF will be common and will be having equations 1 minus e raised to power R T by L. Okay, so let's see here what happening. So 60% of the final value. We can also calculate this way, because we know that in one time constant, because it's one tau, it will be 63% of the final value. It means 6.3 milliampere. Okay, it means t is equal to 8.33 microsecond, because this is the value of tau, yani at time 8.33 microsecond. Now at two time constant, it will be 86% of the final, which is 8.6 milliampere. And how much will be the time? It is the double time because of 2 tau. So it will be yani after 16.7 microsecond, inductor will charge 80.6, milliamp, 8.6 milliampere. Now 3 time constant, 4 time constant, we can calculate like this. All right. So here is a note for you. So how it's become basically short circuit. We know that for DC F is equal to 0, right? So when it is 0, so what will be the XL? You know the formula for XL? 2 pi FL. So F is 0. So when the frequency is 0, XL will be 0. Getting? So for DC, okay, the XL will be 0. And which type of battery we are connecting? DC. That's why what happening? The XL is 0. So inductor will behave as a short circuit and pass the DC. So for the DC, inductor behave as a short circuit and it pass all the DC. So because we are applying here a DC battery, so we can simply calculate the final current Vs over R. This is the reason which is mentioned here. All right. Okay, let's see this one. So same question can here can also be calculated by this way, means by this equation. Okay, another alternative way to solve the same question. Just keep putting the value like final current and keep calculating that way. So now again we can consider, instead of connecting the battery, removing the battery, if we connect here a square wave. So what happened with the square wave? Any capacitor will be charging when the pulse is high, and when the pulse is low, capacitor will be discharging. It's just these slides are showing the concept. Okay, so we can say that when the we have the high pulse, so we can see what happening, the because here we are not looking for the current, here we are looking for the voltage. So what is the relation here? Because of we know that when it is high, so what happened, here the voltage will be developed. And how much voltage? Because of the current is flowing, right? So voltage will develop. We can calculate that one. So here initially we said that any when the current is increasing, okay, so with that time current increasing means what? Like the resistance is basically decreasing, right? That's why the current is increasing. So when resistance keep on decreasing, becomes zero, it means at that time voltage developed here will be maximum voltage. Are you getting? So this is the concept here, which we can see what happened. Just a minute. uh, okay, just a minute. Okay, yeah. So here the graph is basically not the current graph, it is a voltage graph, right? So what happening during that time, when the voltage is applied here, so we have Vs source voltage, and the VL voltage is keep on decreasing, because initially what happened, the inductor behaves like a open circuit. So the voltage which is developed here, it is the same voltage which is you are applying. But with that time, what happened? Its resistance keep on decreasing. That's why current keep on increasing. Getting? So when resistance keep on decreasing, it means the voltage also keep on decreasing. It's like that, and it reached to zero during when it keep to maximum. Okay, and it means is that the current will be the highest this time. So current and voltage relationships are basically inverse. As the current is increasing, it means what happening? Yani it's increasing because of the resistance is decreasing. When the resistance decrease, definitely voltage will also decrease across the inductor. It's like that. So here during that time, inductor basically charge fully, and when it is fully charged, it allows all the current flow through it. So we can see that it is fully charged now. So when it is fully charged, it means the voltage it is become like a short circuit, and because of the short circuit there is no voltage across this one, which you can see like 0 volts. Now when this zero comes, half cycle, when the supply voltage is zero, and that time what happened, inductor start discharging. So initial current is very high because it stored the current, and it start reducing, and it keeps to zero because of the current is high, if current is high, so definitely voltage will be also high in the beginning and keep reducing the current. So voltage also keep reducing. Okay, so this is the charging and discharging of voltage of the inductor here. So half time it's charged, half time it discharged. We can see this one. So here we can have a close look now, because previous slide we only discussed the voltage, but see, we can also discuss the current, and the current shape is exactly same as the voltage shape in the capacitor, like rising exponential and decreasing exponential, right? But the voltage is opposite to that one, because we know that initially the resistance is very high, and because of that reason the voltage developed across the resistance inductor is high, and it's keep on reducing. And when the current is high means what? Yani the resistance is zero. Because of the resistance zero, voltage is also zero. Okay, so this shape is exactly same shape which we have seen that for the capacitor charge and discharge. All right. Now, inductive reactance formula is same as we discussed for the capacitance. XL in total will be the sum of individual reactances. And then we can calculate, and this is the formula, and we can apply and we can calculate. It's a sum. We can calculate this. For the parallel, a reciprocal of the sum of reciprocal formula, and we can also calculate that one. All right. Same formula which we use for the capacitive inductance. So here determine the RMS current. See, the voltage given is RMS. So we can also calculate the RMS current. So first of all, we need to calculate the XL, because F is given, L is given. Let's calculate the XL. XL is coming 6283. After that, we can just apply the Ohm's law. IRMS will be VRMS over XL. XL, as I said when I was teaching this RC circuits, that the formula, Ohm's formula are same. So you can use VRMS over XL, which is 5 over this, and we are getting 769 micro ampere. So here is the rule of the any voltage and currents. So we have seen, for if just recalling with the RC circuit, we have seen that the currents leads the voltage by 90 in capacitor. But here is opposite. Current lags inductor voltage by 90. Okay, which is there. So just need to understand, in RC circuit, we said that current leads by 90. In RL circuit, or we are saying simply the current lags the inductor voltage by 90. All right. So power in inductors, we have seen that because of how the inductor is created by having a long wire. And if we have a wire, it means is that there will be a wire resistance itself. So that's why we have a true power in the inductor. Okay, so ideally inductor do not dissipate the power. However, a small amount of power dissipated in the winding resistance because of the equation. So actually it's charge and discharge. So there is ideally no power dissipated, but because of there is a long wire, we make a coil there, helix. So because of it, the long wire length, there is a small winding resistance created in a small winding resistance, and there will be a strong small a true power, which is a true power can be calculated IRMS square into RW. So RW is the winding resistance. Then definitely we have a reactive power similar to the in the capacitor. So PR VRMS into IRMS, or VRMS square over XL, or IMR square into XL. Anyone we can use. A unit is again VAR. Okay, reactive power, volt ampere reactive. So here is the question: 10 volt RMS signal with the frequency. This is applied to 10 millihenry coil with a winding resistance of 5 ohm. See, the winding resistance is given, oh, and the value is just 5 ohm because of it's very low. Determine the reactive power VR and the true power. Okay, so for the true power we need winding resistance, but for that we need current IRMS. So for the current, what we do first, we need to calculate the XL. After calculating the XL, divide this VRMS by the XL to get the IRMS, and then we can continue. So first get this, then get the I, this one, then use the equation for the reactive power, I square into XL, this is the right one, and P true will be I square into RW, and we are getting this true power. All right. So there's one more thing associated with the inductor, which we call the quality factor, or denoted by the Q. So quality factor of a coil is given by the ratio of the reactive power to the true power. So what is a quality factor? It is just a ratio of reactive power to the true power. So Q will be I square into XL, which is PR over PT, okay, P true. So I square into RW. And now you can say I square will cancel. So Q factor can also be written as XL over R, inductive reactance over the winding resistance. So this is called the quality factor. So by this, we just completed this chapter. We have inductor, we have some definition, winding, the loop or tungsten wire indicates this one. Voltage produced by result of changing the magnetic field is called the induced voltage, inductance, and then Henry. So these are some keywords, some definitions. So you can just look and revise this one. Then quality factor, the ratio of reactive power to the true power. All right. So this way we have done with this chapter. All right. So the next chapter will be discussing the RL circuit. So now the chapter number 11 is completed.